감사합니다. Okay, so I was told to give the talk in English, so my talk will be in English. So thank you very much for the invitation and the opportunity to speak here. And thank you very much for the very flattering introduction, which I don't know if I can live up to, but anyways. As Professor Pyun explained, it's a great honor. It's difficult to explain in words how much it means to me to stand here to give a talk, because I was undergraduate here. I'm more used to sitting there and seeing, professors speak. But yeah, I don't know if I can do this, but let's see. So today, what I would like to talk about is black holes. So black holes are perhaps the most celebrated predictions of Einstein's theory of general relativity. What is a black hole? A black hole, by definition, is a region of space-time where the gravity is so strong that not even light can escape from it. So you see, by definition, actually, this is precisely the region where we cannot see or receive any signals from, right? So there's no way to measure what's happening inside a black hole. But still, we can ask the question, what happens inside of it? And what we can do is we can, at least in the context of Einstein's theory of general relativity, probe what is going to happen inside a black hole, using mathematical methods, right? So that will be what I would like to do in this talk. Okay, so since this is a math talk, let me start with some introductory definitions, okay? So in the following, 10, 15 minutes, I want to spend some time to explain to you sort of give you a very quick crash course on general relativity. Okay, so what is general relativity? Let me first explain the kinetics, okay? So by kinematics, what I mean is, let me try to explain to you how motion are described in the context of general relativity, okay? So in general relativity, the space-time is described by a 3+1 dimensional or 4-dimensional manifold. Which is equipped with what's called a Lorentzian metric. Which is analogous to a Riemannian metric, except that when restricted to each tangent space, the signature of this metric is minus plus 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 instead of the all plus, which is the case of Riemannian metric. Okay? So the key fundamental example that you want to keep in mind is the case of the Minkowski space. This is the canonical example of a Lorentzian manifold. So in this case, the manifold M is nothing but R4, okay? And the metric, which I'll write as G naught, is given by the following form. Where you see in one direction, the metric will give you a negative sign value, whereas in other directions it will give you a positive sign value. So if this were plus, then this would just have been the 4-dimensional Euclidean space, right? But because there's a minus sign here, because the signature is minus plus plus plus, this is this describes different geometry, and it's called a Minkowski space. Now, using this metric, we can classify types of tangent vectors. Okay, so the significance of this will become more clear later, but let me just describe to you, start with the definition for the moment. So let me try to plot the Minkowski space, where the vertical axis is the x naught direction, and the other directions are represented by the other variables. Okay, okay, let's use the Minkowski space as a example. I can classify the tangent vectors, or in this picture, just the points in this plot, into three types. depending on what is the value of the metric applied to the vector v. Okay, so I'm taking a vector v, and then I'm evaluating what happens when I plug in v and v into this metric. Okay, so the region, so there will be a region where this value will be 0. Okay, because there are different signs. In this case, we call v a null vector. Okay, and in this picture, null vectors form a cone that looks like this. Okay, so I'll call this a null cone from now on. And then if you look at vectors which lie inside of these of this cone, which are things like this, I've drawn it so that gives you the value negative when you plug this into the metric. And in this case, v is called time-like. Well, you can see it in the slide over there. And when the vector lies outside of the cone, this value is positive. In this case, v is called space-like. So far, this is just the classification of types of vectors. And then now, what are the relevance of these? The relevance is as follows. So in general relativity, we describe the motion of an object, which is free falling, by which I mean there's no force acting on it except the effect of gravity. These things are described by a time-like geodesic. Okay, so as in the case of Riemannian geometry, with a Lorentzian metric, you can form the notion of covariant derivative, and also you can form the notion of geodesics. And among the geodesics, you can find geodesics whose tangent vectors are time-like. These are called time-like geodesics, and these are precisely things that describe the motion of a point-like particle with mass. Okay, so in the case of Minkowski space, this will be just straight lines whose angle with the vertical axis is less than that of this cone. Okay, and then moreover, general relativity says that the motion of massless particles, of which the most important example is light, is described by a null geodesic, which means a geodesic whose tangent vector is null. Okay, so these, in the case of Minkowski space, are simply straight lines whose angle with the vertical axis is, as I've drawn, 45 degrees. Okay, whose tangent vector lies here. Okay, finally, I can describe to you now how gravity is modeled how gravity is described in general relativity. So gravity is described by the curvature of the space-time. Okay, and what does it mean more precisely? Well, if you recall, elementary differential geometry, you remember that the curvature enters in what's called the Jacobi equation, which describes the relative acceleration of if you take a bundle, you take a family of geodesics, okay, and then you think about the infinitesimal variation through these geodesics, okay. So you can think of this as describing the relative acceleration among these infinitely close geodesics, okay. And this gives you a vector field, which I call y. It's often called a Jacobi field, along a fixed geodesic. And the Jacobi equation tells you how you can compute this Jacobi field, right? So it models the relative acceleration of geodesics. And there, the curvature tensor appears through what's called the Jacobi equation. I think I want to put a sign minus, but it doesn't really matter. Okay, so in other words, this is how you should think about, this is how gravity is modeled, described in general relativity. It describes the relative acceleration of nearby geodesics, or in other words, tidal acceleration among nearby geodesics. Any questions so far? Okay, so far I've told you how motion are described in relativity. Now let me tell you the dynamics of general relativity. That is to say, let me describe to you the equation of motion of general relativity. So this is the famous equation that's been written down by Einstein more than 100 years ago, called the Einstein's gravitational field equation. So in a nutshell, it describes how gravity, that is to say curvature quantities of the space-time, is related to the energy and matter distribution in the space-time, which is this right-hand side. Okay? So more formally, the left-hand side consists of the Ricci curvature minus 1/2 the metric times the scalar curvature. I don't want to get into the precise definitions of these, but you just should think that this is some quantity that's constructed from the space-time curvature tensor, okay, which enters from you see from this Jacobi equation. And on the other hand, on the right-hand side, we see an object which is called the energy momentum stress tensor, which I'll call T. Okay, and this is supposed to model the distribution of energy, momentum, and stress. So in other words, distribution of matter content of the space-time. Okay, so this is something that you can compute, this is coming from the matter. Okay, and for those of you who are more physically inclined, let me just say from the outset that I'm setting the physical constants, the gravitation constant, and the speed of light to be 1. Okay, so you won't see these constants in this talk anymore. So this Einstein's gravitational field equation is the generalization of Newton's law of universal gravitation. Okay, so it tells you how gravity is caused by matter. But then you and I've written it in the following form. So I've written in the form of for the gravitational potential, right? And remember, Newton's law of universal gravitation tells you that the Laplacian of the gravitational potential is given by some constant times the mass density, which I call rho. However, there are some conspicuous differences that you can spot between the Einstein's equation and the Newton's law of universal gravitation. First of all, it's a bit hard to explain, but let me say that the type, so both are some sort of PDE, but then the type of the equation, the type of the PDE is very different from Einstein's equation to Newton's law. So to the leading order, the solutions to the vacuum Einstein equation, so vacuum means I'm going to set this to be 0, is not like the Laplace equation, which would be when you set this equal to 0, but rather like the linear wave equation. Okay? So this is actually the reason for the term gravitational wave. So gravity field itself, propagates like a wave. And on the other hand, it also tells you that the correct problem to ask for a Einstein equation is that of the initial value problem. So in the case of Newton's law of universal gravitation, what you want to ask is, okay, given some mass distribution, you want to ask what's the gravitational field, right? You compute from it directly. But on the other hand, in the case of Einstein's gravitational field equation, that's not the problem you want to ask. You want to ask, there is some initial condition for the gravitational field, and then you want to ask, how does it evolve in time? Okay? And another conspicuous thing, difference that I want to spot between the Einstein's equation and Newton's law is that the Einstein equation is nonlinear as opposed to Newton's law. So this means that even in the vacuum case, okay, of course, this admits a trivial solution. So I should have said the Minkowski space here is, of course, a solution to the Einstein equation with t equal to 0, to the vacuum case. But because of the nonlinearity, so roughly speaking, that means that the gravity field itself actually feeds back into, it causes gravity. And that causes Einstein's equation to admit many, many more interesting solutions other than just the trivial solution, which is not the case in the case of Newton's law. So let me give you the first example of a non-trivial solution to the Einstein equation. It's called the Schwarzschild solution. So this is a solution to the Einstein equation, which is spherically symmetric. So actually, it's quite remarkable how quickly it was discovered. So it was discovered in the same year. So it was published 1 year after, but actually it was discovered the same year as Einstein published his equation by Karl Schwarzschild, while actually he was serving in the military during First World War. in the First World War. Yeah, actually, I'm also doing my military service. So this is a very high bar to, to aim. But anyway, so it's actually not very difficult to write down. So the Schwarzschild space-time is actually one parameter family of spacetimes where the where the parameter is some positive integer, positive number m, and it takes the following form. In fact, there's a sense in which all spherical solutions, spherical symmetric solutions of the Einstein equation are of this form. But it's called Birkhoff's theorem, but let me not describe it in some details. Let me just point out a few features. First of all, note that this metric is static. So this t actually will play the role of time in some sense. But you see that the metric is not dependent on t, right? So in other words, this describes a static solution. It's a solution that doesn't change in time, okay? And second, notice that if r is taken to be infinity, then this disappears, and you just get this expression, which is nothing but the polar coordinate expression of the Minkowski metric, where I'm using the letter t for x naught, right? So this means that this metric is asymptotically flat as you go to large R region. So R is the radius, area radius of a sphere of symmetry, of the sphere of symmetry. It tends to the Minkowski space. So the physical interpretation is the following. Because of these properties, the Schwarzschild space-time models the gravitational field in the vacuum region. So this solves the vacuum Einstein equation. So there's of a static, so time independent, spherical symmetric, isolated body. Okay, so isolated body corresponds to the fact that it's asymptotically flat. So it's something that's isolated and nothing, even gravity is there when you go to a far away region, which is the R large region. Does this make sense?
So what is the physical meaning of M?
Okay, I'll get into it. But actually, the physical meaning of m is the mass of this isolated body, which is measured at infinity. Okay. And when you look at this this metric, you realize that there are two singularities. One, when r is equal to 2m. In this case, this becomes a division by 0, so the metric is singular. And the other, when r is equal to 0, when both of these, are when this is bad, right? It turns out that one of the singularity is not a real singularity, but rather just a coordinate singularity. It just looks singular because you've chosen this particular coordinate system. It's just like the coordinate singularity in polar coordinate, r equal to 0. Okay? And in fact, you can continue the metric past r equal to 2m. Okay? On the other hand, r equal to 0 turns out to be a real singularity in the sense that curvature quantities actually blow up. And I will describe to you how the continuation of this Schwarzschild metric looks like. And in order to do that, I want to introduce a way to represent the causal properties of a solution to the Einstein equation, which is called the Penrose diagram. So I want to spend some time to discuss this because this will be very convenient in the ensuing discussion. Okay. So what is the Penrose diagram? It's nothing but a way to represent a space-time. Okay. On a two-dimensional plane, like this blackboard or this slide. Okay, the screen. And first of all, what we do is we note that we know in this case this is a spherically symmetric solution, so the angular dependence is not very interesting, right? So what we're going to do is we're going to drop it. Okay, we're going to fix the angular coordinates, some theta and phi. Okay, and we're just going to plot the t and r in the t/r coordinates the space-time. Okay, and second thing we do is even though we do that. As it is, it's going to be an infinitely extended picture in the TR plane, right? So we cannot represent it in a finite region of the screen or the blackboard. But what we're going to do is we're going to compactify the space-time. Okay? But then we'll do it in a specific way. We're going to compactify through a conformal transformation. And this just means that it's a compactification such that the new metric is just some positive function times the original metric. Okay? And what's the property of this conformal compactification? An important property that we're going to use is that this keeps the causal types of vectors v invariant, right? In other words, if g of vv were negative, then so would be g tilde of vv, and so on, right? If it were 0, then it would be 0, and so on. So if you compactify the Schwarzschild space-time in such a way, then I'm going to use the convention that the null directions are at 45 degrees from the vertical axis. Okay, so if you use this convention, then this is the representation of the Schwarzschild space-time. I need to explain to you a little bit more. So in fact, this point here is the compactified ideal point where r is going to infinity. Okay, and then this region here, which I call E, is precisely the region where r is bigger than 2m. Okay, and this dotted line here is also an ideal boundary that you get by compactification. It's called the null infinity. So this part, this 45 degrees part, is called the null infinity, and this models the ideal limit points of null geodesics, which try to go in the direction where r is increasing. Okay, and the future endpoint, ideal endpoint again, of this null infinity is called the time lag infinity, and it's denoted by I plus. The physical interpretation is as follows. Remember that the Schwarzschild space-time tries to model an isolated body. Okay, so we, as an observer from very far away, will be receiving signals which comes out of the system, right? And signals are carried by, say, light signals, and therefore, what this null infinity represents the possible light signals we can receive from the system from our point of view. Does this make sense? Okay, then, now the interesting thing, it turns out that the Schwarzschild space-time contains what's called a black hole, which is the topic of this talk. And let me try to explain. So it turns out that this r equal to 2m, I told you, is a coordinate singularity, and it can be continued. And this actually just corresponds to a null hypersurface, null curve in this Penrose diagram. And in fact, there's more of the space-time beyond it. But then note that the following property, that if you shoot light from any point inside this region, past this h plus, this r equals 2m region, it can never reach the null infinity, which is where we can receive signal from this system, right? Because light is in this picture it travels in 45 degrees from the vertical axis, right? This is precisely the definition of a black hole region. So this is the region, a black hole region, by definition, is the part of the space-time where light, it cannot emit light to null infinity. Okay? So it turns out that the first solution that's non-trivial solution written down for the Einstein equation actually is a black hole solution. But actually it took much more longer time to realize that this is a black hole solution, like in the, I think, 60s or, but okay. Okay, let me also just say that it turns out that if you extend this in a natural way, say by analytic extension, then the space-time has another asymptotically flat end, which I represented on this side of the space-time. But in this talk, I will not talk too much about this side of the space-time. Okay, so we'll just focus on one side according to this physical interpretation that I try to give. Okay. Right, so far so good. So I've explained to you the Schwarzschild space-time, a non-trivial solution of the vacuum Einstein equation, which turns out to describe a black hole. It took much longer time to find the next non-trivial sort of stationary solution to the vacuum Einstein equation, which is called the KAIST solution. So it was discovered by Roy Kerr in the 60s, 1963. And if you look at the expression of the metric, you can realize why it took so long to find this. Actually, I've not met a person who really, by hand verified that this solves the Einstein equation. It's very hard. I tried, but I didn't go through. I didn't have the patience to do it. But anyways, believe me, this is a solution to the vacuum Einstein equation. Okay. And you can do this. You can play the same game. So in this case, this is asymptotically flat space-time, which models a stationary rotating black hole. Okay, so it doesn't change in time, but it doesn't change in time in the sense that its motion is constant in time. So it models a rotating black hole, and of course it's rotating, so it's not completely spherically symmetric, but nevertheless the dependence on the angles are not as complex, and you can still play the same game of drawing a Penrose diagram to understand the causal properties of this space-time, and it looks like this. Okay, it has also this exterior region, null infinity. There's a region of the space-time which is black hole, so you cannot communicate to I+, and there's also this strange other end, which I'll not focus. Now let's compare these two black hole solutions. Okay, so this is where I want to motivate our discussion of the interior of black holes, which will be the topic of the rest of my talk. So first of all, notice that outside, in the exterior of the black hole, so in the outside region, in the region where you can communicate by light signal with null infinity, the Schwarzschild space-time and Kerr space-time look basically the same. And of course, you would sort of expect this, right? Because after all, I should have said, if you set A equal to 0, A measures the unit angular momentum per mass, I think, per unit mass. If you set A equal to 0, then you get Schwarzschild space-time. And if you turn on A, then you get Kerr space-time. So it's hard to imagine that things outside change very much when you have A equal to 0 or non-zero. However, what's sort of remarkable is that if you look at these explicit solutions, the structure of the interior of the black hole changes significantly depending on whether A is 0 or A is non-zero. So what happens is this. So of course, let me describe it to you the fate of a very brave observer who enters into the black hole. Okay? So in the case of Schwarzschild space-time, if a particle or an observer or an astronaut enters the black hole, then there's only one fate that awaits this poor guy or lady, which is that in finite proper time, so according to the clock of this astronaut, it'll reach this boundary of the space-time, which I'll call S. This is the region where R is equal to 0, where curvature tends to infinity. In other words, this observer will experience infinite tidal force, which will tear this guy apart. I'm sorry, as it approaches this singular region. And this is the only fate that's possible for a particle that enters the black hole. However, in the case of Kerr black hole, whenever A is turned on, something drastically different happens to an observer that enters a black hole. So the common feature would be that this observer would also exit the space-time in finite proper time. However, the boundary of the space-time is very different. I've called it CH+. It's called it stands for Cauchy horizon. Well, for the moment, it's just a name. But what happens is that it turns out that nothing, in the sense of local quantities, is singular at the Cauchy horizon. So this, in the sense of, in mathematical sense, is just a smooth or even analytic boundary of a manifold. So in particular, this gamma A doesn't experience any, drastic tidal force as it exits the space-time. And moreover, it's possible that, it's possible to extend the space-time as a Lorentzian manifold past this CH+ in a regular way, and in a very highly non-unique way, even as a solution to the Einstein equation. In other words, you cannot predict the future of this observer from the initial data of the Einstein equation. So that's what I've stated so far. And and let me just add, although from the point of view of an observer, this scenario is much more preferable, right? You'd rather be, you'd rather explore the brave new world rather than, experience infinite tidal force and being, torn apart. However, from the point of view of theory, this case is much more satisfactory because it at least accounts for the fate of all particles inside this space-time, this solution, right? Whereas here, there's nothing that can be said about the fate of this guy past this boundary from just the classical theory of general relativity. So this, in other words, means that in this curved space-time, the classical notion of determinism breaks down. You cannot determine the fate of all objects in the system by the equation of motion. So this is a bit troublesome from the point of view of theory, but amazingly, nevertheless, the physicist Roger Penrose in 1969 made a very, very brave conjecture that although this is the behavior that we see in explicit solutions, generically, this is a very special situation, and generically, that's what's not happening, and in fact, determinism holds. So that's the content of strong cosmic censorship conjecture. Okay, so it says that this is a mathematical formulation of it: maximum future development of a generic. Okay, generic. So some special counterexamples may exist, and it does exist. It's the Kerr space-time. But if you consider generic asymptotically flat initial data, then it should be inextendable as a suitably regular Lorentzian manifold. We'll later discuss what we mean by suitably regular because this will be a very interesting topic. But for the moment, let me proceed. And this conjecture was made for a very good reason. And this reason is called the blue shift effect of the Cauchy horizon, CH+. And let me try to explain to you a bit what this heuristic is. Okay? So basically, what this heuristic wants to say is that a small perturbation outside the black hole may translate to a catastrophically large effect inside the black hole. And this proceeds as follows. You consider two observers, A and B, one which enters the black hole and exits space-time through Cauchy horizon, and B which remains outside the black hole and just stays. Okay? And suppose that this observer B outside the black hole sends in signals to A by light rays at a rate which is constant according to the clock, to the watch of this observer B. And notice the following thing. This B, because it has not entered the black hole, will live for infinitely long time, so it won't terminate in finite time, right? And therefore, there will be infinitely many signals that B sends into A. On the other hand, A receives all the signals that B sends before leaving the space-time. But the proper time, or the clock, the time that according to the clock of A, is finite before it exits space-time. So therefore, the frequency of the signal must be shifted infinitely to high frequency, or blue, as A passes through the Cauchy horizon, and this is the blue shift effect. Okay? So in more technical terms, it tells you that at the level of optics, geometric optics, there's something, the energy of light ray is magnified as you go to Cauchy horizon. Okay? Now the question I want to ask, the mathematical question I want to ask is, can we see manifestation of this heuristic, blue shift heuristic, at the level of a PDE, or more desirably, a wave equation, because we believe that the Einstein equation is a nonlinear version of the wave equation. Okay, so this is the topic that I want to present to you. And in order to address this problem, I'm going to consider not the full vacuum Einstein equation, but rather a simpler model equation. Okay. So first, simplification is that instead of the rotating black hole KAIST, which had a very complex expression, right, whose metric had a very complex expression, I'll consider a simpler solution called the Reissner-Nordström space-time, which is a spherical symmetric charged black hole. So it's not a solution to the vacuum Einstein equation, but rather it's a solution to the Einstein equation coupled with electromagnetism, with Maxwell's equation. Okay? And M represents the mass of the body, E represents the electric charge of the body, and the metric in the exterior region takes the following form. So you see that it's much, much simpler than KAIST. But on the other hand, its Penrose diagram is basically the same as KAIST. In particular, it also has the smooth or even analytic Cauchy horizon, and also has the same defect of failure of determinism as in KAIST. Okay? So I'll consider this simpler solution instead of KAIST to address this question that I raised. And second, instead of studying the Einstein's equation, which is a highly non-trivial, nonlinear PDE, I'll just consider the simplest example of a wave equation, which is nothing but the wave equation on this space-time, which is defined as follows. So here's the main theorem which answers in positive the question that I raised. It's a theorem, it's joint work with Jonathan Look, who just moved to Stanford this September. And the theorem reads as follows. A generic solution phi to this linear scalar wave equation blows up near every point on the Cauchy horizon, in the sense that if you look at the derivative of phi, and if you look at its L2 norm on any neighborhood of a point on this Cauchy horizon, which I call O, it does not belong to L2. So in other words, it's not integrable, its square is not integrable in this region. Note that a solution can never blow up in the interior, right? Because it's just a solution to the linear wave equation. So the only point where you can blow up points are along the boundary, and we say that it does blow up at the Cauchy horizon. And moreover, I need to explain to you what I mean by generic. Our notion of genericity is formulated in terms of the initial value problem formulation, okay? Consistent with the natural problem to pose for the Einstein equation. That is to say, of course, there will be solutions to the wave equation where the conclusion fails. The simple example is phi equal to 0, right? Then it doesn't blow up here. But then what we say is that you give me any solution that fails the conclusion of this theorem. Then I look at the initial data on the initial hypersurface of this space-time. Then I can give you a perturbation of this data, which I call phi sing, which is smooth and compactly supported. So if you're in PDE, this means that it belongs to basically any reasonable function space that you want to consider, such that if you add just epsilon times this perturbation, then as long as epsilon is non-zero, the solution corresponding to this data blows up in the sense that's described in this theorem. Okay, so I have neither the time or good means to describe to you the details of the proof, but let me just give you some remarks on this theorem that I just stated. Well, in fact, as expected, so the main mechanism for proving this is the blue shift effect that I described in terms of light rays. And as expected from that heuristic, not all components of the derivative of phi blows up. It's only the transversal direction to the Cauchy horizon that blows up. And it's rigorously proven, actually, by complementary stability theorems by Anna Frentzen, and also proved by different methods by Hintz and Vashi, which reads as follows. If the initial data phi is nice, smooth and suitably decaying, then in fact, phi, although we expect generically is singular in this sense, it's stable, it's bounded, actually it's even continuous, all the way to the Cauchy horizon. And moreover, the same conclusion holds for all tangential derivatives of phi. So all derivatives which are angular, which is not represented in this picture, or parallel to this CH plus. Okay, so it's only the transversal derivative that blows up. And second, this is a bit more technical point, but let me try to express it anyways. Our proof, the idea of our proof is to first show that a generic solution to the wave equation obeys some lower bound on the boundary of the interior of the black hole, which I call H plus. It's called the event horizon. Okay, so what I want to prove is that generically, so given any data, I can perturb it a little bit so that the solution to the wave equation with this perturbation has some lower bound along this event horizon. Okay, so in fact, as a corollary, actually, we verified that the heuristic decay rates of the solution to the wave equation posed by a physicist, which is called Price's law, is generically sharp. So it's attained as a lower bound. And I should say that without this restriction, there were previous work which showed this blow-up result at the Cauchy horizon. So it's really the genericity that sort of sets apart our work. So I've told you that we verify some lower bound along the event horizon. And then what we say is that from here, the blue shift mechanism that I roughly described takes place. And that translates this lower bound on phi on the event horizon to this blow up at the Cauchy horizon. But in fact, so this was sort of known by a previous result of Diformis. But in fact, we had to strengthen this because we could not prove the lower bound, which is consistent with Diformis's criterion. So these were sort of two main technical steps of our proof. Okay, so I'll just end the discussion of my talk by discussing the implication of the result that I presented in the full nonlinear problem. Okay, so the natural question to ask is, okay, I told you of a result which takes place in a model situation, right? But what we were really interested in was the Kerr solution for the vacuum Einstein equation. And we can ask how much of the picture that I described for the linear wave equation on Weierstrass-Nordström stay true for the full nonlinear problem. And in fact, there was a very, very remarkable recent work that was announced by Diformis and Look, which tells you that at least the stability bit of the picture that I described, that is to say, this theorem of Franzen and Hintz-Vashi, stay true in the full nonlinear setting. So the precise statement will be something like this. Suppose that we know that the exterior, so you consider the Kerr space-time, okay? And suppose that we know the stability of the exterior of the black hole. So this is not yet proven, but as far as I know, nobody really doubts the validity of this statement. And in fact, this is a very actively pursued direction in mathematical GR. People are trying to prove this. But suppose that stability of this region, okay, exterior region of the black hole space-time, of Kerr space-time is known, okay? Then it'll tell you that, some initial perturbation here tells you, leads to some decay property of the metric, right? Along the event horizon, which is the boundary of the interior and the exterior of the black hole. Given that, Dafromus and Luck proved that, in fact, the metric is stable in C0 sense all the way up to the Cauchy horizon. So, in other words, the analog of this theorem is true, where phi, the role of phi is played by the metric G. So this brings us back to and in particular, they say that small perturbations of Kerr are still extendable as a C0 Lorentzian manifold, as a Lorentzian manifold with C0 metric. So actually, this is a negative answer to the strong cosmic censorship conjecture. When by suitably regular, one means C0. So this result tells you that you have to be careful when you formulate this notion of suitably regular. And this was a big surprise, actually, because it was believed this C0 formulation was one of the prominent formulations that was believed before. But on the other hand, our result suggests that maybe the strong cosmic censorship should be formulated in the following way, that by suitably regular, we mean that the metric does not belong to, belongs to the Sobolev space W12. In other words, this is a space where derivatives of G would be in L2. So our result tells our result, if you interpret phi as an analog of the metric G, is consistent with the conjecture that even though we have the stability result, inextendability, generic inextendability might hold in the sense of G, derivative G belonging to L2. And let me just conclude by remarking that, with the remark that G, the derivative of G belonging to L2 is actually the minimal requirement for formulating even a weak notion of a weak solution to the Einstein equation. If you want to, so therefore, if this formulation holds true, then this means that you cannot meaningfully extend the space-time as a solution to the Einstein equation, generically. And let me also say that this formulation is consistent with the picture that was suggested by the physics literature, their famous work of Poisson, Israel, and Ori, which were obtained by studying the Einstein null dust model, where null dust basically are systems of ODEs, which travel in the null direction. And let me also say that this is also consistent with the previous mathematical work of Dafromus and Dafromus-Rodniansky on a different model problem for this problem, which I'll not explain, but just mention. Okay, thank you very much for listening.